Okay, so integration by substitution is kind of like the chain rule for integrating. It's not quite the chain rule because it's not as straightforward, but you use it in the same kind of ways. So we've actually done the type, well, a little bit of the type of problem that we would see integration by substitution. For example, let's say I have, so just to give you a really simple example, let's say I have something like this, let's say. So notice that we don't have, so in our table that we came up with for antiderivatives, we have the antiderivative of cosine of x, right? What is the antiderivative of cosine of x? It's just sine of x, right? Okay. But what about cosine of x plus 4? Well, we could probably guess and check, can't we? Well, probably it has to have a sign, right? There's no other way to get cosine. Has to have sign. What has to be inside of parentheses?
X plus 4.
You have to have an x plus 4, right? Okay. And would you, yeah, well, you have to have a plus c, right? But is that it? Like, are we done? Is that the antiderivative? So like if I get the derivative, if I test, if I get the derivative of sine of x plus 4, what do I get cosine of x plus 4? Yes or no? Sure you do, right? So we just found it by guessing, right? So we didn't do any fancy technique. We just said, well, I don't know what it is, but well, I guessed and I got it right. Good job. Okay, now let's do one similar. Let's say I have 2x plus 4. Is this the same thing? So notice this is a little bit different, right? Having the 2 in there changes things. Because here, notice if I do my test, if I get the derivative, so notice what do I get? Cosine of 2x plus 4, what? Times 2. So now this is not correct, right? So we've done this before though, right? So we actually are able to fix this. What would we do? What would we do to our antiderivative? How would we change it to fix this? Just divide it by 2, right? So if I say my antiderivative is 1/2 sine of 2x plus 4, then when I get the antiderivative of that, what would happen? The 2's would cancel, right? And so that would change this x into a check, and now I'm good to go, right? Okay, so notice there was no need for any special technique, but we did have to be a little bit careful. So let's say we do another one. I don't know, maybe a little bit harder, I guess. Let's say we have 2x times cosine of x squared plus 4. Oh, I forgot the dx there. That's not good. Okay. So this looks quite a bit different. Because notice I'm multiplying two functions, right? I'm multiplying 2x times cosine of x squared plus 4. But do you guys have any guesses? If you were going to give it your best shot. Well, it's going to have a sign, right? For sure. There's no other way to do it without having a sign. What has to be inside of sign? X squared plus 4, right? There's nothing else that could be in there. Because when you get the derivative of it, it stays the same. So it has to be in there. Okay, Now, well, and then plus c, right? And then you might think to, I don't know, divide it by 2x or something, but that actually would not lead you very far, because what would you get if you start getting the derivative of something like that? It turns into a mess, right? So you would have to use the quotient rule and all kinds of stuff. But, so I want you guys to observe something. Observe. If I just leave it like that, what happens when I get the derivative of sine of x squared plus 4? You get the cosine x squared plus 4 times 2x, right? Which is actually, it turns out, exactly what I was looking to get, right? So that was kind of a lucky guess. I just made up the problem so that we would get lucky. But there's a key thing to observe here. And this is the key to most of the integration by substitution. So note that you have this here inside. So the inside of your parentheses here, the inside function, when we tested the derivative to see if we got that function, we have to, by the chain rule, get the derivative of that inside, right? Okay. So notice that the derivative of that, the derivative of the inside is right there, the 2x. Meaning if you look at the inside, x squared plus 4, and you get its derivative, that's in the integral multiplying your function. And that is something that you want to look out for. If you see that, you say, okay, so you have some stuff inside, right? If you get its derivative and you notice it's multiplying your function on the outside, then that's like go full speed ahead, integration by substitution, which we'll talk about in a little bit. But it's kind of like this idea where by the chain rule, when you got the derivative of it, notice that you got that 2x that you didn't really know what to do with. So like here, for example, let's do another one that's kind of similar. Let's say, for example, you had, oh, I don't know, x to the 4th times e to the x to the 5th. Okay, so here, if we think of our inside, that we call it, what would the inside be? X to the 5th, right? Because that's inside the exponent. So my main function here is e. This is the kind of the inside function, right? Okay, what do you notice about the derivative of that? It's 5x to the 4th. And we'll see that the 5 in front doesn't really affect much. We can easily fix that. But this right here, the fact that we found x to the 4th and it's right there, that tells us, hey, we can easily integrate this without a problem. What would it be? Well, we can do this one kind of guessing a little bit like we did the other one. If we just think of the antiderivative of e to the x, it's just itself, right? And then, well, we're going to need a plus c, right? And this is almost correct. Almost, almost, almost. What are we missing? Times what? Times 1/5, right? We're going to need a 1/5 to balance out this extra 5 that we're going to get. Now you can see that if you do a little test, right? So like if you go, oh, let me test. What's the derivative of e to the x to the 5th? You would get e to the x to the 5th times 5x to the 4th, right? So there you see, oh, I need to divide by 5, right? That's where the 1/5 comes from. So I needed to divide by 5, or multiply by 1/5 so that the 5's cancel out. Does that make sense? Okay, so one more guessing check. So let's try one more. Let's see. How about secant squared of square root of x over square root of x? Okay, so here if we give it our best guess, we're going to say tangent, right? Because tangent's the antiderivative of secant. We know we need a square root of x in here, right? And then we notice that the derivative of square root of x is 1 over 2 root x, which we almost have in there, right? Okay, so let's just kind of start off there and get the derivative of tangent of square root of x, and then we can put in any constants if we need them, right? So here, what would I have? I would have the derivative of this is secant squared root x times 1 over 2 root x, right? Okay, now is that right or wrong? Right or wrong? Well, right. Is it right, almost right, or wrong, wrong? Almost right, right? What is it off by? It's off by this 2, right? So what do we need? We just need a 2 on top, right? And the 2's cancel, and now we're good to go. So that was pretty easy, right? Okay. Now, this is only because I made them so that they're easy. So it's not always going to be this easy. But notice that this would be impossible for us, at least right now. If I, for example, just do a small change to, let's say I just kind of leave that the same and then put an x down here instead, for example. This all of a sudden becomes not doable. So notice it's not a very big change, but we can't do anything with this really, because anything that we come up with, so notice this is non-negotiable. We need to have this because there's no other way to get secant squared of square root of x. But getting the derivative of tangent of root x doesn't give us the x on the bottom, right? But anything else that you put in there will just make it worse. So if it's wrong up to a constant, it's easy to fix. If it's wrong with other variables, then it is either more difficult, meaning you have to do some more stuff, or not possible with the current amount of knowledge you have. Because, for example, let's just say hypothetically you say, oh, well, I need another root x down there, so I'm just going to put it in. Well, now that's a problem, right? Because what happens when you get the derivative of tangent root x over root x? Quotient rule, it's going to turn into a big mess. It's not going to turn out to be anything close to that. What else can you do? Well, I don't know. You can try a whole bunch of stuff, but nothing's going to work probably. So you're kind of stuck. Okay, so that's why we kind of want a series of steps or a strategy that will help us integrate not only when it's obvious what to do, because these are pretty easy. You know, once I kind of showed you guys how to look at them, you're like, oh yeah, I can do this. But if it's not as obvious, then you kind of need a more structured strategy to figure it out. So let's do that. So integration by substitution. And this is kind of just the sort of the basic strategy. So let's do an example here. Let me see. Okay, let's do something like this. Okay. So, all right. So the first thing you want to do is you want to choose the substitution. And almost always, not always, so this is kind of like the what you do most of the time, and then I'll show you some other cases that are a little bit funky. But your substitution is almost always the inside of your function. So like you have some stuff inside the integral. Almost always, whatever is inside a function is going to be what you substitute. So like right here, if you look at this, notice how you have the square root function, and you have 5 plus x to the fourth is inside, right? Okay, so that you call u, almost always is the letter you use. So you let u be inside. Okay. And again, it doesn't have to be the inside of something, but most of the time that's what it's going to be. Okay? All right. Then the second thing you want to do is find du. Okay, so to find du, if u is equal to, in this case, 5 plus x to the fourth, then du, so I'll do it in 2 steps this time, and then we'll do it in 1 step the next time. But so you find du by first finding the derivative of u, which is what? 4x cubed, right? Okay, and so then du is 4x to the third dx. So you find it by solving for du right here. Does that make sense? Okay, now here you have kind of 2 options. I'll show you the way that I typically like to do it. And then I'll kind of give you the alternatives here. But you basically want to substitute the original integral. So you only have u's, and dx turns into du. Okay. U's. U's. U apostrophe S. U's, you know? Okay, so you're going to do so that's what it's called, integration by substitution. So you're changing all the x's into u's. So, okay, so what you do is, so see how you have u is 5 plus x to the fourth? So I'm going to substitute 5 plus x to the fourth there. In for u. So let me rewrite it here. Okay, so this is equal to the integral. Okay, so there I just substituted 5 plus x to the fourth in for u. Okay, now the other thing that I need to substitute is I have this x cubed and then I have dx. Now so I need to change the x cubed dx into u's. How do I do that? Well, I have here that du is equal to 4x cubed dx. So can I substitute the two orange items? Can I substitute x cubed dx for du? Yes, no, or almost? Almost, right? What do I need? 4, right? So typically what you do is you say, okay, well, I'm going to multiply by 4 and divide by 4. Is that okay to do? To multiply and divide by the same number? Sure it is, right? Okay, so now notice that if I take 4x cubed dx, is that not exactly equal to du? Yes or no? So everything I just circled right there. So what am I left with if I do that? If I substitute those three things that I circled for du, what else am I left with? A 4 on the bottom, right? A 1/4. Does that make sense? Are you with me? Does that make sense? Yes, no, maybe? Okay, so now I have 1/4 times the integral of the square root of u du. Now, do I know how to integrate that? Do I know the antiderivative of the square root of u? Should be pretty easy, isn't it? What's the antiderivative of... So I'm just going to leave the 1/4 there. But what's the antiderivative of square root of u? That's u to the 3/2, right? We just add 1 to the exponent times 2/3 plus c, right? So let's write down that step. Step 4, integrate. Step 5, go back to the original variable. Meaning go back to what u was equal to before. So what was u equal to before? 5 plus x to the 4th, right? So u is 5 plus x to the 4th. And then to the 3/2, right? Plus c. And then if we simplify the 1/4 times the 2/3, what would that be? 1/6, right? And that's the antiderivative. Does that look right? Well, we can always test, right? If I get the derivative of 1/6, 5 plus x to the 4th to the 3/2, I'll leave off the plus c just for space. What do I end up with? This would be 1/6 times 3/2, right? Times 5 plus x to the 4th to the 1/2, and then times what else? 4x cubed, right? Is that equal to what I started off with? It is, right? This is 4 times 3 is 12 divided by 12. That cancels out. So I have 5 plus x to the 4th to the 1/2 times x cubed. So it's a matter of just substituting. And how did we know that this was going to work from the very, very beginning? We were pretty sure. Why were we pretty sure? Because the derivative of the inside of the radical, what is it? 4x cubed. Notice how we have the x cubed right there? So then that told us, hey, this is going to work. you know. So that's like the easiest case kind of thing. The most obvious case that you need to use integration by substitution is you have some inside, its derivative is out there ignoring any constants, and so then you move full speed ahead with substitution. I want to show you another option. This seems a little bit strange right now, but once you practice it, it's not that bad. But let me show you another option for the option 2 for the substitution part. So it's worth just kind of having both in your brain. So I'm going to take the same exact problem. So we have this right here, right? And we have u, we said, is 5 plus x to the 4th. And du is equal to 4x cubed dx. Okay, so the way we did it is we substituted 5 plus x to the 4th. We substituted it for u, right? And then we looked at what was left, and we tried to change all the x's into u's. We tried to substitute the du in there. And at first, that feels a little bit weird. So this might be a little bit easier, maybe. So let me show you. So instead of that, when you get to this step, solve for dx instead. So if I solve for dx, what would I get? Du over 4x cubed. Okay. So what you do at this point is you say, okay, well, I'm going to substitute u right here. And I'm going to substitute dx right here. And you hope that everything cancels out and you're left with only u's. Okay? So we hope. All right. So off we go. You ready? So we have x cubed, square root of what? U, right? And then instead of dx, what am I going to put down? Du over 4x cubed. And then you simplify. So if I simplify here, what can I get rid of? X cubed cancels out with x cubed. And then am I left with only u's? Yes. So is this good or bad? This is good, right? So now I have square root of u over 4 du. And then this is same as before. So did you guys see the difference between the two? So it's not completely different. It's just that kind of middle part, the du and the dx part, where you do that. You solve for dx instead, and you just plug it in, and you hope that it works out. Which, if you pick the right technique, which is nice because right now we only have one technique, basically, integration by substitution. So it'll work out. Any questions about that? No? Okay. All right, you guys want to try one? Okay, so here, what's going to be my u? 1 over x, right? So then du, the derivative of 1 over x, is going to be minus 1 over x squared, right? Because 1 over x is x to the minus 1, so if you get the derivative of that, you get minus x to the minus 2, which is minus 1 over x squared. Okay, so notice that minus 1 over x squared, oh, and then minus 1 over x squared dx, right? Yeah? So notice that you have a minus 1 over x squared dx here, except for the minus 1 part, right? So depending on what option you're going to use, so For example, if you were going to say, try to substitute minus 1 over x squared dx for du, you would say, okay, well, I have a dx over x squared right here, right? So what's the only part I need? I still need a minus 1, right? So then I need to balance it out by, you could say divide by minus 1, but it's the same as multiplying by minus 1. So, and that works fine. And then here you would have 1 over x is your u, right? So then if I do the substitution, then what would this be? This would be equal to minus the integral of sine of u du, right? Does that make sense?
Why is it just du? Dx.
So this right here, minus 1 over x squared dx, that's du right there. Everything in the orange circle. So I already had the dx over x squared. I just multiplied it by a minus 1. If you're following the option 2 route, which some of you might have, you would have done this. You would have said, okay, sine of 1 over x. So how many of you guys did option 2? Okay, nobody. Okay, all right. So what you would have gotten is sine of u, because that's your substitution, right? You would have solved for dx here. Dx would equal to minus x squared du, right? So if I replace dx with minus x squared du, like that, then notice the x squareds cancel, right? And you end up with the integral of minus the integral of sine of u du, which is exactly the same thing, right? Does that make sense? Okay, now what's the antiderivative of sine, just sine of u? Careful with your signs. It's not cosine. It's minus cosine, right? Because it's backwards from the derivative. So because I have a minus here already, this is going to be positive cosine of u, right? So just be careful with your signs. So, because remember, they're backwards. So notice if I get the derivative of cosine, I get minus sine, which is what you're looking for, right? Okay, and then what's the last step? Go back, yeah, back substitute, right? To what u is equal to, which is 1 over x, and then plus c.
It's really hard to see. On option 2, I understand the x squareds cancel out. I don't see it the same way on the first one. I'm having a hard time.
That's why it's an option. You can do it whichever way you want. It really doesn't matter. So if option 2 seems more natural, then go with option 2. For some really tricky problems, option 2 is almost the only way to go. So,
but what you're saying in the first option is du equals dx over x squared, but just in a negative.
well,
By negative.
yes. Meaning that it's kind of like you look at what you have and you want to substitute it with du, but you don't quite have it. You have it almost. So you need to multiply and divide by a constant to get it to substitute. In this case, it's minus 1. And the other problem was 4, I think, right? Any other questions? You want to do another one?
I'm kind of confused. What happens with the du?
Nothing. Because remember, it's part of the integral. So the du is much like the dx. So if I'm going to substitute and change everything into u's, then I have to have du. Just for the same reason that over here you have to have the dx. And do you remember what the dx represents? From back in the day, a few lectures ago. What is the dx? Where is it from? Where does it come from? What does it represent? You guys remember? Like where does this dx come from? Why does every single integral we do have a dx? It does mean it's with respect to x, but where does it come from? Well, it's a good thing you asked then. Okay, so you guys remember this, right? Okay, so what is this equal to? All right, what goes inside the sum? F of x sub I times delta x, right? Okay, so remember that what this dx represents is this delta x is the width of the rectangles, right? And what happens as n goes to infinity? What happens to the width of the rectangles? It goes to 0, right? It gets infinitely small. So that's what the dx represents. It's the infinitely small width of the rectangle, basically, for us. So that's why you always have it. It's part of the definition. So you don't do anything with it, but you need to have it there, and it has to be the same variable that you're integrating with respect to. So it would not make sense, for example, if I end up with the integral of, say, 2x du, this is a big fat sad face. You cannot do that. That makes no sense. If you end up with something like that and there's no way around it, then you made a mistake somewhere, because it makes no sense. So this is sad face right here. Does that make sense? Okay. Any other questions? No? You guys are good? All right. All right, so what'd you guys get? What's your substitution? Okay. So I'm going to tell you one thing that you should never, ever, 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 ever do. You guys ready? Never let u equal x. Ever. Why not? I'm going to show you why not. What is du? It would be 1 dx. Okay, do the substitution. What would you get? What did I just do? Did nothing. I did absolutely nothing. I have the same exact integral with a different letter in it. Might as well just write the integral of 2 hearts divided by, or sorry, d heart over 2 heart. Or the integral of d circle over 2 circle. Or I don't know. What else could I do? D doodle over 2 doodle. Because you're just doodling, right? We're not doing anything. Okay, so never do that. Okay, never. Okay, so there's only one thing you can really make u equal to here.
1 over x?
Well, okay, maybe not. Okay. This will be a good exercise. Okay, 1 over x, right? I'll tell you now this is wrong, but let's do it anyways, because it's a good exercise. Okay, so what's the one of the very first things we said when we said, okay, well, this tells you whether substitution's definitely going to work or not. If, what about u? Do you guys remember? If the derivative of u is also in the integral, remember that? So what's the derivative? If u is 1 over x, what's the derivative of u? Minus 1 over x squared. Okay, so do you also have that? In addition to the u, do you also have the du in there? No, right? So this should produce some sadness and probably, maybe not sadness, just a revisit to the original substitution that you tried. So that's okay. I mean, you'll see that as you practice more, you'll see that you make a lot of mistakes because it's not easy to know what to do. So there's one more thing we can try. 2x. Yep. Now this doesn't seem like it gets us anywhere, but it does give us something because what's du? It's just 2 dx, right? And well, although it seems too simple, like we don't really gain much, let's try it anyway. So my 2x is gonna change to u, right? Do I have a 2 dx? Almost, right? So if I multiply by 2 and then divide by 2, I can do that, right? Those two balance each other out. Multiply and divide by 2, yes? Okay. Then what is 2 dx equal to? That's du, right? Okay. So then what do I end up with? I end up with 1/2 times the integral of du over u. I'm going to write it in a little bit more obvious way. I think that'll help you recognize what that is. What is that? Do we know the antiderivative of 1 over u? Yep, it's natural log, right? Isn't that the natural log? Plus c, which is just 1/2 natural log of 2x, right? And that's it. So that wasn't actually that bad, right? So it looked harder than it was. Or I guess it looked easy, but then it was confusing. So that's another thing that happens. As you learn more, you start getting confused in your brain too. Because things that used to be easy all of a sudden become hard because your brain knows more, so then it thinks everything is harder than it is, and so sometimes you get confused. So be ready for that too. Okay. So any questions about that one? No? Let's see. All right. So, I'm going to, let's see, right here. Maybe just to remind you here of a couple of things. Let's see. What's that? It's the antiderivative of 1 over the square root of 1 minus u squared. Inverse sine. Yep. Okay. What about, so make sure you know these. These are very important. Oh, sorry. I'll use u just to make it a little bit clearer. What about 1 over u squared du? That's inverse tangent. And 1 over u times square root of u squared minus 1. Inverse secant, that's right. Okay, so these three are important to know. So then, for example, let's say you have the integral of 1 over 1 plus 4x squared dx. So notice this isn't really your typical substitution because if we were just kind of thinking of the kinds of problems we've been doing so far, what would we think of as our u to be? Well, I've heard like 3 different things, but maybe 1 plus 4x squared, or maybe 4x squared, or maybe x squared, right? So those are 3 things that I heard. But actually none of those work because notice if I get the derivative of any of these, is the derivative in the integral? It's not, right? So for example, if I change the problem, so I'm not going to, but let's just thought experiment. If I had an x up there, what would be a good substitution for that problem? Any of them would work, but probably the best one would be the first one, 1 plus 4x squared. Because if you get rid of the whole denominator, change it into a u, notice the derivative of 1 plus 4x squared is just 8x, and you have an an x up there. So then that would work, right? Does that make sense? Do you guys see that, how that would work? So if you don't quite see how that works, try that one, this one right here, with u equals 1 plus 4x squared, and see that it would work. But if I have a 1, then none of those substitutions work, right? Because I wouldn't be able to get rid of the dx. So do you guys want to see that, how it doesn't work? You guys interested in seeing that? Let's try it just for fun. Okay, so this doesn't work, but let's just kind of work it through just a little bit. So let's say u is 1 plus 4x squared. What would du be? 8x dx, right? Okay, so let's do option 2 just to make it a little bit easier for us to see maybe. If I solve for dx here, I would get du over 8x, right? So then what would this integral be? It would be the integral of 1 dx is du over 8x, right? And then 1 plus 4x squared, I said I would change it into u. Do you guys see the problem? I can't have x's and u's in the integral. It's not possible to integrate it. Do you see of anything else you can do to get rid of the x? Change it into a u. Well, you could solve for x here. What would you get? U minus 1 over 4 square root. Okay, so then, well, that works, right? Now you have the integral of 1 over u du over 8 times the square root of u minus 1 over 4. Does that look great or what? No, right? Okay. All right. So you see how this is not very good. Okay, so this is what it looks like when substitution doesn't work. Okay, so now we go, okay, well, there's a reason why I put a recap over here on the side. If you look at the integral and you compare it to these guys over here, does it look like anything over there on the right? Kind of looks like the second one, right? Kind of looks like the inverse tangent. Well, so then if I'm thinking, okay, well, it almost looks like 1 over 1 plus u squared, right? if that's kind of where I want to go, what would you have to be? Not 4x. 2x, right? Wouldn't it have to be 2x? Because when you square it, you're going to square the 2 and the x, right? Okay, but you have to make sure that all the pieces fit together, meaning that the du and the dx business, so the dx has to change into a du, right? So what is du? It's 2dx, right? Well, does that work out? Sure it does, right? Because let's say you solve for dx here, you would get du over 2. So if I change the dx for a du over 2, does that look pretty nice? I would say it looks pretty nice. Because what does that equal to? What's the antiderivative of that? What do I do with this 2? Yeah, just take it out, right? So this is just 1/2 times what? Inverse tangent of u plus c, right? Which is 1/2 inverse tangent of 2x plus c. And that's it. Does that make sense? So it's a little crazy, right? A little bit crazy. Do you guys want to try one?
Can you explain again?
Yes, go ahead.
Determine dx needs to be du over 2.
Well, no, I solved for dx on this one instead. So I used option 2. If you want to do it with option 1, you would just go right here. You would say, okay, well, I need a 2 dx, so you would multiply by 2 and then divide by 2, like that. And you end up with the same thing, right? Because the 2 dx is equal to du, and then you still have the 1/2 on the outside. So it's just a slightly different way of looking at it. Once you do it a few times, you'll be able to easily go back and forth between the two options. And sometimes one is more convenient than the other, but it's kind of a whatever floats your boat kind of thing. Any other questions? Yes.
Can you go back to the part where du equals 2dx?
Well, okay, so here, this is also one of those things that it's difficult because it isn't. So you get the derivative, right? What's the derivative of 2x? 2, right? So then if you solve for du, you get 2 dx. And that's it. Yes?
Why is it 2x and not 4x?
Because what you're trying to do is you're trying to make it to look like this, the inverse tangent that you know the antiderivative of. So you know the antiderivative of 1 over 1 plus u squared is inverse tangent, right? So you know that, so then you want to make, you want to turn this 4x squared into a u squared. So then you need to think, okay, well, what does u have to be for me to make that substitution? Well, u would have to be 2x. Or basically, you would have to get the square root of 4x squared, right? Essentially. Because you're going to square it, and you need to end up with 4x squared. Does that make sense? Yeah.
Why is it half inverse tangent and not 2 inverse tangent? If you multiply the 2 on the outside, you cancel it out, but then it's half.
Yeah, because So du, remember, is 2dx. So this 2dx, we substitute it for du. So the 1/2 is the one that stays. Does that make sense? So the 2 that was on top gets substituted into du, and then the 1/2 is still there. Any other questions? So it's tricky, right? Tricky. Okay. All right. So it's your turn. You ready? How about the integral of 1 over the square root of 1 minus 8x squared. All right, so what did you guys get for u? Root 8x, right? Yeah. Root 8x. Why? Because you're going towards this integral, right? Because you know the antiderivative of that is inverse sine of u, right? So what would u have to equal to? Well, it's just the square root of 8x squared, which is square root of 8x. And then just make sure that everything else falls into place, right? So du, what would that equal to? Root 8 dx, right? So then what would I need? I would need a root 8 on top and a root 8 on the bottom, like that, right? So then the root 8 dx is equal to du. So that's this du right here in the orange. The 8x squared, that's u squared. And what am I missing? On the right side, the right integral. Just the 1 over square root of 8, right? Does that make sense? That substitution? So what does that equal to? That's inverse sine of u over square root of 8, right? Plus c, which is inverse sine of square root of 8x plus c over root 8. What do you guys think?
Are you saying that you plug in root 8 where du is, or where dx is, because du equals root 8?
No, I multiplied top and bottom by root 8 in that case. But you could have also instead solved for dx and gotten du over root 8 and substituted that in for dx, and you would have gotten the same thing. Any other questions? No? You sure? Okay. All right. Are you ready? What about that? Okay, so, all right, let's think about this a little bit. So this is where we're going, right? You guys agree with that? Yeah. Okay, so we have a couple of problems here. Well, the major problem is the 9. It has to be a 1. There's no way around it. So how do you get rid of the 9? well, you can factor, right? So so it's a little bit of funny factoring because you need to factor out a 9, which is fine to factor out a 9 from a 9, but what about the x squared? Yeah, it would be x squared over 9, like that, right? Okay. So, well, okay, so let's do, let me write the square root here still. So it looks like that, right? Now, notice you have the square root of 9 times 1 minus x squared over 9. So, do you guys agree that I can get the square root of 9 and take it out as a 3? That's okay, right? All right, because they're multiplying, so that's okay. And then I have 1 minus. So, this is kind of what I want. I need to figure out what goes in the parentheses there, because that's going to be my u, right? It's going to be x over 3, exactly. Right? So it's basically, I mean, it's the same thing, right? It's the square root of x squared over 9, which is x over 3. So that's what you let u be. U is x over 3. So then, what's du going to be? One-third dx, right? Do you guys agree with that? Okay, so so I think maybe we would benefit from doing this in 2 steps. So let me erase that first for a little. Okay, so let me rewrite. So I'm going to have, this is equal to the integral of, so I have 1 here, right? And then I have 3 down here, the square root of 1 minus x over 3 squared, and then dx, like that. So does that make sense? That's what we have? Okay, so then let's do our substitution here then. So x over 3 is u, right? And then what about du? So du is 1/3 dx. Do I have a 1/3 dx? Do I need to put anything there? So what do you notice? What's that? What's the dx over the 3? That's exactly equal to du, right? So dx over 3 is exactly equal to du, right? So do you guys agree that this is equal to the integral of 1 over the square root of 1 minus u squared du? Yes or no? Sure it is, right? Which is equal to inverse sine of u, right? Which is inverse sine of x over 3 plus c, right? Does that make sense? All right, so questions? No?
Yes.
Yes, go ahead.
So, the second step where you circle the 3 is du.
Uh-huh.
So, that's after we factored it out.
Yep.
And don't we plug du into dx?
You mean, if you prefer, sure. Yeah, I mean, it's just a matter of, I think you prefer option 2, but everybody else prefers option 1. That's why I've been sticking with option 1. But that's all right.
I understand.
It's okay. You don't like option 1. That's fine. What is dx equal to? 3 du, right? So if I replace dx with 3 du, what do you notice happens with the 3's? Oh my gosh. That's not what. The 3's cancel, right? And so you end up with du over square root of 1 minus u squared. Which is exactly the same thing. So again, it's whatever floats your boat. No big deal. Either option 1 or option 2. Okay, questions? No? Okay. All right. What about no, not x cubed. What about this one? All right, so even when you're not sure if substitution is going to work, another thing you should look at is see if there's any algebra you can do to change it, maybe. But there isn't really anything you can do here, right? Since you're given this problem in Calculus 1, well, there's only one thing it could be. It has to be substitution because you don't learn any other techniques. So substitution it is. So what do? You just try to go forward anyways. So that's probably what most of you guys wrote down, right? Because that's the inside of the radical, so that's kind of the obvious choice. If you did u is x squared, that's okay, but it wouldn't get you anywhere. But then, okay, so then what's du? Dx. Okay. So if I substitute here, you'll notice that I have the square root of u, right, which is nice, and then du, right, because dx is equal to du. But then I have this little problem of this pesky x squared. All right, so what you can do, though, is then once you get here, you can ask yourself, hey, well, I wonder if I can write this in terms of u. And do you guys see any way that you can change x squared into u's instead? You can solve for x, right? In the original substitution, if u is x plus 4, x is u minus 4, isn't it? So then this is then equal to the integral of u minus 4 squared times the square root of u du. And does that look doable? Doesn't look great, but it's definitely doable, right? Because, let me write it down again. So u minus 4 squared, square root of u. If you look at it quickly, it kind of looks the same as the original one, but it's not really, because what can you do with u minus 4 squared that you couldn't do with the square root that you originally had? Yeah, you can FOIL it out, right? So u minus 4 squared is the same as u squared minus 8u plus 16, right? Times square root of u, or let's just write it as u to the 1/2. And then you can distribute the u to the 1/2 in here, right? So then what would that be? U to the 5/2, right? Minus 8u to the 3/2 plus 16u to the 1/2. That's a little bit of work, but that's completely doable, right? I mean, that's a pretty easy antiderivative. We've done this quite a bit before. What does that equal to? U to the 7/2, right? Times 2/7 minus u to the 5/2 times 2/5, right? But there's an 8 there already, so 16/5. And then plus u to the 3/2, right? And then I have 16 times 2/3, so that's going to be 32/3 plus c. And then last but not least, just go back to x plus 4, right? Plus 4 to the 3/2 and then plus c. So you're not always going to know from the very beginning that it's going to work out, but you know, you try it anyways, and then sometimes you need to, you know, kind of take a step and then reevaluate. Okay, well, is there any way to kind of salvage this? And this is something that's relatively common that happens. Yeah? Thumbs up all around. Okay, questions? No? You sure? All right. Okay. All right, give it a go. So what'd you guys think? Any ideas? U equals e to the x. That's a good choice. That is a good choice. Why u equals e to the x? Well, it's a little bit difficult to see, but if you rewrite, if you use the laws of exponents, you can rewrite e to the 2x as e to the x quantity squared, right? So, well, that now kind of looks like inverse tangent a little bit, right? Because then what would du equal to? E to the x dx, right? And notice that e to the x dx is exactly right there, right? That substitutes right away. And this is u. So this turns into exactly 1 over 1 plus u squared du, right? Just like that. So this is one of those that it's easy to do it once you know what to do, which is always the hardest part, is knowing what to do. But it's also the most fun part. It's the part where you have to think. So you end up with inverse tangent of e to the x plus c. Tricky, right? What do you guys think? Fun times, right? Integration by substitution is fun. Okay. All right, how about do it together? All right, so any thoughts, any ideas? Well, you could, but you would end up with a fraction. I don't think that would help. So one of the problems with this is there are kind of a lot of paths to try. And if you're lucky, maybe you would, I mean, if you have no idea what to do and you just start trying stuff, in the best case, you'll get lucky and you'll do the right thing from the beginning. But the most likely thing is you'll just do a bunch of stuff and never really get anywhere. So like, for example, like if you try to use identities, so these are all things that you probably shouldn't necessarily write down, but so if I, for example, use the Pythagorean identity, so I have this, right? Sine squared x is 1 minus cosine squared x, so I can't really use that one, right? So that's no good. I know that sine of 2x is 2 sine x cosine x. So that looks like it might be useful, right? But then notice if I change the numerator into a sine 2x, will that help me integrate it any better than no, right? Not really. But if you just kind of, let's say we remove identities from the picture, what do you notice about the numerator and the denominator?
Both have cosine.
They do both have cosines, yeah. What if you do, so would for example, like an inverse tangent kind of a deal work? Like if I let u be cosine x to try to get 1 plus u squared on the bottom, would that work? Should we try it just for fun? What would du be? Negative sine x dx. Okay, so then what is that equal to? Well, that's going to be 1 plus u squared on the bottom, right? On top, I have dx and then a minus. So if I put a minus and a minus there, that would be minus du, right? And then what else do I have? I still have a cosine x, right? Was there anything I can do there? Well, what's cosine x? Cosine x is u, actually. So, did that get me anywhere? Well, it's not inverse tangent, right? But that actually doesn't look that bad, because what do you notice there? If you now compare the numerator and the denominator, what do you notice? So like, for example, if I forget about the original problem and I say, okay, well, this is your problem. Could you do that? Should be able to do that from, I don't know, maybe half an hour into the class. Maybe right now you're tired, so maybe it doesn't quite come to you. But what would you do there? How would you integrate that? Hint, it's an easy one. Don't have to do anything fancy. It is substitution, but what would it be? I'll pick another letter because I already have U there, so I'll pick W. So it's like a second substitution, which is okay. So what would my W be? You can't take variables outside of the integral. You can take constants out, but not variables. So notice that if I let w be 1 plus u squared, what's the derivative of that? 2u, and notice that that's in the integral, right? So the derivative of this, which is 2u du, notice is almost exactly that right there, right? What's the only thing that I'm missing? A 2, right? So I would put a 2 here, 1/2 on the outside. So 2u du is dw, and then the denominator is just w. So then this is equal to minus 1/2 the integral of dw over w. And what's the antiderivative of that? What is it? No substitution. That's just ln of w, right? Because it's the same as 1 over w dw, right? So since we did 2 substitutions, well, we just need to go back twice, right? So this is going to be minus 1/2 ln of 1 plus u squared plus c, right? Which is minus 1/2 ln of 1 plus cosine squared x plus c. Wowzers. Look at that. Now, anytime you do 2 substitutions, that means that you actually could have done the original problem with just 1 substitution. So we won't do it, but I'll let you guys do it for fun. You do for fun with 1 sub. What would the u be? Can you guys see now what it would be? Yeah, exactly. If you let u be 1 plus cosine squared x, notice what's the derivative of 1 plus cosine squared x? 2, so you do the chain rule, right? So 2 cosine x times negative sine x, right? Which is in the numerator, right? So it would be like doing the 2 substitutions that we just did, just in one step, right? So that's one of the things that happens, that is that, besides from there's trig all over the place, so then it's scary. But you start learning things, and then you think it's more complicated than it is. I mean, this one's a little bit complicated anyways, but once you know what to do, notice it's not really that bad, right? Granted, once you know what to do. But that's why the hardest part is knowing what to do. And that's why you need to practice a lot. Lots of practice. So highly recommend, after you go through all the video ones, always try them on your own first. But then just crack open the book, go to substitution, and just go down the whole list and try to do all of them. And when it gets easy, then you're good. Yeah. Okay. All right.